In this video, we are going to demonstrate how to assess for confounding in multiple linear regression model in STATA. At this point, I expect you to have already assessed for the different assumptions of linear regression. You have chosen which variables to include into your model, and you have also assessed for interaction effects amongst your independent variables. We have got separate videos that go into details of how to do this in STATA. Be sure to check it out. To understand confounding, let us consider a very basic example. Suppose you want to study the relationship between exercise and systolic blood pressure. But you think age may influence the relationship between exercise and systolic blood pressure. So age would be a confounder because older people tend to exercise less. So it is related to the exposure or independent variable. But also, age directly increases blood pressure. So it is related to your outcome variable, systolic blood pressure. If you do not adjust for age, it may look like exercise has a bigger effect on blood pressure than it actually does, because age is entangled between exercise and the systolic blood pressure. That's why it is very important for you to check for confounding. Otherwise, you will reach to conclusions that either a variable is significant or not, which may not be true or may be misleading. Here is a hypothetical dataset that we want to use to demonstrate how to check for confounding in linear regression. We have our outcome variable, which is systolic blood pressure, and we have got 5 independent variables. We have 3 which are numeric, and we have 2 which are binary categorical variables. We want to determine factors associated with systolic blood pressure. If we wanted to assess whether smoking is a confounder in this dataset, then we are going to first run a model without smoking, and that model will be the crude model to give us the crude coefficients. Then we run a model with smoking included, and we shall call that adjusted model to give us the adjusted coefficients. And then we compare the crude and the adjusted. We see whether there is any change above 10% for any of the coefficients of the variables in the model. So we shall start by fitting the crude multiple linear regression model through statistics, linear models and related, then linear models. In this dialog box, we shall put in the dependent variable, which is systolic blood pressure, and our independent variables, age, BMI, exercise, and gender. Because we are adjusting for smoking status in the crude model, we do not put that variable there. So we shall click OK. So this is our crude model with the crude coefficients. We shall also run the adjusted model that has that variable we are assessing for confounding. Still, we shall go to statistics, linear models and related, regression, and then we now add a variable called smoking status onto it, and then we click OK. Yes, you'll see that now our model has the variable smoking status or smokers. That is the adjusted model, and it has the adjusted coefficients. So the coefficients we are comparing, for example, age, initially age was 0.772, whereas right now it is 0.769. We want to see what was the percentage change, similar to the rest of the variables. I have prepared here an Excel to help us with quickly calculating this. We have here our crude model where we just picked the coefficients. Here, they are the ones pasted here, and then the adjusted coefficients from this model with the smoking status here. We then calculated the percentage change using the formula crude coefficients minus adjusted coefficients over crude times 100 to get the percentage change. You can see that between the crude and the adjusted, the changes were really not that big. They were all less than 10%, implying that our variable smoking status is not confounding a relationship between any of these variables with the systolic blood pressure. But if we had, for example, here, maybe 15%, it would show that smoking status confounds the relationship between gender and systolic blood pressure. And therefore, that variable will be in our model, whether significant or not, but it will stay in the model as a confounder. So that's the basic principle of checking for confounding in linear regression. But simple as it is, there is a new problem. Out of the very many variables that are in my dataset, which one should I start with checking for confounding? Which one should come last? To answer this question, we have to be very clear about our research objective. Do we have a main exposure in our study, or we do not have a main exposure? If we do not have a main exposure, for example, if our question is what are the factors associated with systolic blood pressure, then we shall check for confounding for all the independent variables. How do we do it? We start with variables that are non-significant, and to obtain them, we use stepwise approaches in STATA. To use stepwise approaches to help us identify those non-significant variables, we simply go to statistics, go to other, and then choose stepwise estimation. In this dialog box, we specify which type of regression we are running. Here we are running linear regression. That is it is command. Then we have the dependent variable, which is systolic blood pressure, and we add terms or the independent variables in this dialog box by clicking on add, and then you put term 1 is age, click OK. You go add another term, another independent variable is BMI, click OK. I'm really very lazy to use this term to finish all the variables, assuming you have got very many variables. Really, it will be tiresome, but I just demonstrated to you to know where to get that command, so that we add the rest of the variables once we have the command in the command window. So we shall specify the level of significance or the p-value where we want, above which the variables should be eliminated from the model, those that are non-significant. So we shall click on significance level and we specify 0.05. That's the usual alpha value, and then we click OK. From this, you can see that we didn't add all the variables, but I was interested in the command here. I click on it, it comes here in the command window, and then I add the rest of the variables. I think this is easier. So we put in all the independent variables and we enter. So you'll find that this model starts with all the variables and it keeps dropping those that are not significant. From this, we see that it has removed smoking status because the p-value was above 0.05, which we specified. So if you have several variables, you'll find that they have removed several of them here. So you start checking for confounding with the one that appears last on the list. And from this, you can see that it is smoking that has been dropped. So where we have no main exposure, we are going to assess for confounding exactly the way we have done, fitting a model without smoking. So this would be our crude model. If you remember, this is what we obtained previously as our crude model here. Then we then run a linear regression model with smoking status to obtain the adjusted model, which we've already run here, the one having smoking status, and we obtain, then we go through the same calculation. So that's scenario 1, how to check for confounding, which variables to start with if you have no main exposure. However, if you have a main exposure, then you assess for confounding even for significant variables in your model, but only against the main exposure. Your interest is to know, are these variables in my final model as independent variables, or are they also remaining there as confounding the relationship with the outcome? Remember, for a scenario where we did not have a main exposure, we were only determining confounding for non-significant variables. So assuming age was our main exposure, then it means we shall not be calculating the percentage change up to down here. We only calculate percentage change for each variable, that is, for example, smoking status, only with the main exposure. If a variable is found to be a confounder, then that variable is going to be part of your final model as you report your results. If you found this video useful, consider liking and subscribing to the channel so that you don't miss out any of our next episodes. Next, we are looking at the final step of linear regression, interpreting the outputs of multiple linear regression analysis. We shall be interpreting the coefficients for the numerical and categorical variables, as well as the model goodness of fit, plus other parameters that come with the linear regression analysis output. See you in the next episode.